Okay, so I am going to recording as well. Can you see my slides?
Yes.
Yes.
In between, if you have anything, any issue, please stop me anywhere, right? Don't raise your hand. Maybe I cannot see, but you can speak out. Okay, right? Does any participant want to come? No. That's all. So we have to start now. Okay, Bismillahirrahmanirrahim. Good morning and Assalamu alaikum to all. So this, because this course have combinations of organic chemistry plus physical chemistry, right? So the initial 4 lectures, the 2 lectures already taken by Dr. Hanis, right? So this and my 2 lectures, the chemical thermodynamics, these 4 lectures are from the physicochemical. Previously, we have different courses, physicochemical and organic chemistry, but we have merged. So 4 lectures from there. The rest of the lectures will be from the organic chemistry. So my lecture is about the chemical thermodynamics. So you have to have idea what is chemical thermodynamics and what is the implication or application of this chemical thermodynamics in your pharmacy. Okay. I can. Okay. So thermodynamics, what is its relevance in pharmacy practice? What is the application of law of thermodynamics in pharmacy? Later we will go through by the laws of thermodynamics, thermodynamics law 1, 2, and 3. But 3 I will not do it. Maybe I will go until only second law of thermodynamics, inshallah. Thermodynamics is one of the most vital subjects in science, without which the imagination of the whole universe seems to be impossible. Why it is vital? Because all of this going around you, all the process around you, inside your body, all belongs to thermodynamics, right? For example, if you have cup of tea, hot cup of tea, for example, you go some restaurant, you have hot cup of tea on your table, and after, when you touch, it's very hot. After 15 minutes or 20 minutes, when you forgot, oh, I forgot to take my tea or something, or maybe you don't want to take tea now. After some time, you will see your cup of tea. When you touch your cup of tea, it's not very hot, it's cold. So what happens? It becomes the heat inside the cup is transferred to the surrounding, right? Or you can say from the outer side is cold and the inner side is hot. So it's a transfer of heat. So we will see either this is transferred from the cup to the surrounding or surrounding to the cup. Okay. So all these things, and when you take any medicines, sorry. So when you take any medicines, oral medicine, right? Your tablets, your capsules. So how it goes into body and absorbs, right? And it works. All this phenomena comes under thermodynamics. That's why it is a lot of applications in pharmacy, because you, as a pharmacist, you're dealing with the medicines, right? So you should know what happened, which type of medicine is a good application as an absorption in our body or bioavailability. This all you should know. And all this belongs to thermodynamic, right? When it comes to pharmacy, the criteria is like stability of sample. So when we take the medicines, right, it's not just take the medicine and we just say, oh, I will be recovered. No, you should know, because if randomly I have few medicine in my hand and I take A, B, C, and I give A to the one patient, B another patient, C another patient. So the one A I give to one patient, he has no changes. He still has, for example, he has still have fever or pain. The B I give to another patient, he feel little better. When I give they want to come inside. Okay. And when I give the C medicine, the different A, B, C are different medicine, right? C I give to another patient. All the three patients have same problems, right? So when I give C medicine to third patient, so he recover very soon. The A medicine, the patient which take A medicine have no recovery. The B medicine, the patient took have slow recovery, and the C medicine, the patient take have very good recovery. So why the three patients have the same problems, but and the medicine A, B, C are different? So what is the problem with the medicines, right? Either there may be few problems, either all the medicine A and B are not very potent like medicine C, and maybe the medicine A, B are very potent, but they have stability issues. They have bioavailability issues, right? Stability means when we take orally, they are not stable. They just broke or we can say it unstable, right? Decompose orally before it goes inside in our stomach or it works. So it have stability issues as well, right? Or maybe it's not potent, or maybe it's not bioavailable. Okay, if it is stable, for example, it goes inside, but it doesn't solubilize, it doesn't absorb in our body. Okay, so the medicine should have all these properties, have good stability, it has good bioavailability as well, right? Okay, so it's the solubility of the drug, micellization. Micellization means when we take medicine, for example, when you wash your clothes, right? You use detergents, right? And you have water. So all your water and your detergent should be micellized, should be interact with each other. Okay. Once the water and your detergent or your soap is micellized, then it can remove the stain or dirtiness from your clothes or your body, right? So this micellization is also important. Same thing is required for the drug. So drug should have micellization, should be solubility, and drug receptor interactions. Okay, the drug is stable, drug is solubilized, it can be have good solubility, it can be good micellization, and goes inside your body, it reaches the body, right? So the area where it has to react and reduce your pain, your inflammation, or your different disorder. For example, if the person have diabetes or any other issues, so the drug should be interact with your enzymes. The drug enzymes interact, because once the drug interact with your enzymes, okay, then it can inhibit the enzymes, right? Okay, once it inhibits the enzymes, then it can inhibit the overexpression of enzyme, and you can reduce your pain, inflammation, or whatever problems you have. So drug should have three main property: solubility, stability, micellization is also included in the solubility and stability, and drug, the main, and the last is drug receptor interactions. So all it should be, so all this should be included in thermodynamics terms, right? Okay. Okay. So pharmaceutical thermodynamics. In thermodynamics, pharmaceutical thermodynamics is the chemical thermodynamic study of the drugs. So how we study drugs, solubility, stability, and drug interaction, all this comes under pharmaceutical thermodynamics, right? And it includes absorptions, crystallization, encapsulation. So how we make it as a good drugs, right? So it can be a well drug receptor thermodynamics. We should study its absorptions, crystallization, and encapsulation and partition as well. Drug receptor thermodynamics is the study of the entropy, enthalpy, and free energy. Later, we will have discuss this one in detail. What is entropy, what is enthalpy, and free energy. For the right now, you don't understand what is entropy, enthalpy, and free energy. But at the end of this two lectures, you should have idea what is entropy, enthalpy, and free energy, how it relates with drug receptor thermodynamics, right? Okay. And all this comes under drug receptor interactions, right? Okay. A key aspect of pharmaceutical thermodynamics is focus on the pharmaceutical system, as a thermodynamic system. Okay. So all this pharmaceutical thermodynamics is considered as a focus on thermodynamic system. So why should we have should know about all these informations as based on thermodynamics of the drugs or thermodynamic pharmaceuticals? Why? Because the research is going on and people are working to explore many compounds, right? They're working to explore many compounds, right? And they want to explore the drugs. Because when the science is going on, the new drugs are, because when you see the internet or this time, for example, the COVID, right? Sometimes people say they have bug and they have come out with new drugs. And for the COVID, we have many injection vaccines, right? We have Moderna, we have Pfizer, we have Sinovac, and we have AstraZeneca, right? So they are different from each other, right? They are different from each other. Same, different countries, different peoples are working to explore more drugs from the natural products. They are isolated from the plants. It is isolated from the fungal fungus. So all these are natural products, and they are synthesizing as well. Okay. So we have full of drugs, but all these drugs are not working well, right? They have to go many stages. They have to go many stages, right? Well, with the goal of producing more efficacious new chemical entities. New chemical entities, new, when initially there are new chemical entities, and later after clinical phase and so many steps, we have one single drug, right? Okay. The use of high throughput screening the drug discovery space has resulted in a massive increase of hydrophobic compounds. Because when we isolate, or the researchers isolate, initially they don't care about the solubility, right? If the drug is not soluble, it is called hydrophobic. What is hydrophobic means? Hydro means water, phobic means not soluble, right? It's white, right? Hydrophilic means hydro, water, philic means water loving. Or hydrophobic, phobic, reverse. For example, I'm phobic of height, I'm phobic of water. Same process in water. So we have 90% of this natural new chemical entities. They are identified as a being poorly water solubles, right? If you discover the drugs or compound, and they are compounds, not drugs, we say compound, and they are not water solubles, no point, right? No point. Okay. And if they are not water soluble, they are resulting in poor oral bioavailability. Bioavailability means absorption of drugs in your body. If they are if outside they are not water soluble, it means they will also have problem as a poor bioavailability in your body, because in your body you don't have the ethanol, alcohol, not organic solvent. In your body, what do you have? You have water, right? You have water. So all this drugs should have good bioavailability. If they have good water solubility, it will have good bioavailability, right? Okay. So how to overcome this issue? Because we have isolated a lot of compound, we have discovered a lot of compound, and we want to have this one as a good drug. So how we can convert them in a good drugs? So we have to cope with all these problems, water solubility, right? Okay. So there are many ways in which we can convert our non-soluble or hydrophobic compound or poorly water-soluble compound into a hydrophilic or good soluble compound. We can increase the solubility, and at the end we can increase the bioavailability, right? How we can do? So there are few methods. For example, super saturating drug delivery system are formulation approaches that have been developed to overcome these solubility issues. So this solubility issue, someone asked question, maybe Vita, I will reply your question, right? We just finish. Let me finish this 2-3 slides. Okay. Super saturating delivery systems are formulation approaches. So super saturation delivery systems, this is a system by this approach we can overcome the solubility issues, okay, and enhance the oral bioavailability. Super drugs delivery system is a promising concept to obtain adequate oral bioavailability. By this phenomena, by this system, by this configuration system, we can enhance the oral bioavailability, right? And this super drug delivery system contains the drug in a high energy or otherwise rapidly dissolve. If it has a high energy, because drug also need energy to absorb in our body, right? Okay. So any work we done, right, we need energy, right? If you are not have energy, just so you can not do any work. Same, the drug also need energy to absorb in our body, right? Okay. That's why always the doctors say most of the medicine salipas makan, right? After you take your food, you take your medicine, but don't immediately after you're taking your food. After you take food, after half an hour. Why? Because it takes around half an hour, 40 minutes to absorb, to digest your food. And when the food is digested, right? Okay, then it release energy. And the drugs which we take, they use the energy and they can absorb. Right? Okay. The amorphous solid, okay. So how it works, the STDs, how it works, the amorphous solid dispersions are an example of, so SDGs have one field, one key amorphous solid. This is examples of, this comes under ASDS, or amorphous solid dispersions come under super saturating drug delivery system. We already have 176 students. Wow. So this configuration, okay, we will, okay. Amorphous solid dispersion are, this is the examples of super drug delivery system and their success in the increasing, and it helps in the increasing of oral bioavailability, right? And the literature also shows that this amorphous solid dispersion can increase the bioavailability via super saturating drug delivery systems, right? Okay. The success of this amorphous solid dispersion depends on its solid state stability. The drug should be stable at solid state throughout the processing, right? And storage period. If so, storage periods, because if we form the drugs and we just keep in our, because when we prepare the drugs in the pharmaceuticals, we don't even eat at once or within a few days. Okay, it should have some shelf life, right? When you have the drug, you just see manufacturing date and the expiry date. It has some shelf life. So these drugs also have some storage period, right? Okay, at least 2 or 3 years. Some drugs have only 1 year, right? Depends. After 1 year, they just throw or they just check, and if they still can work, so they just extend the expiry period for 6 months or 3 months. So this success of this amorphous solid dispersion depends on the solid state stability throughout the processing. When the process, if they are doing this, the drug is going through this amorphous solid dispersion process, the drug should be stable, right? Okay, I will tell you what is this amorphous solid dispersion, right? Okay, as well as its supersaturation stability, okay, in solution, because when we take in our bodies, it is in the solution forms, okay, and then it goes inside, because we take drug, we just take a water, it becomes solution, and then it goes into our GI environment, our intestine, right? And it dissolves and works, and it absorbs and it interacts with the receptors and works at the end. So the drug which is going to be for ASD, it should be stable throughout all these processes. Okay, so what is amorphous solid dispersion, right? It is defined as dispersion of drugs in a solid matrix, where the matrix was either small molecules or polymer. The dispersed state has included many forms. Okay, so what we do the drug, when we take the capsules or medicines from the doctor or from the pharmacy, your drug is not the drug is inside. The drug is coated with. They coated the drug with some polymers, with some molecules, and they choose the molecules which helps the drugs which is inside this cover. The cover, for example, the capsule is cover, right? It also encapsulation. This is the cover is also is a part of this amorphous solid dispersion, and sometimes you have tablets or capsules in amorphous form, right? So this is a coating. This is plain shiny. Sometimes coating here. The drug is actually inside the upper. You have layer. This layer is the due to amorphous solid dispersion, right? This covering material, usually they choose small molecules or polymer, right? Okay, and the dispersed states has included many forms. For example, you can have mixtures, crystalline, gas, solution. Sometimes you have syrup as well, right? Okay, so what they do, you can see this picture here. Okay, so this is your active drug is this one, API, right? And you use any polymer, and you mix this polymer, right, this gray color, with your active, the is pink color, right? This is your active drug, and you mix, and then you have amorphous solid dispersion. So this is the examples of amorphous solid dispersion. So this is your molecule, API, your actual drug. You mix it with any polymer, right? The polymer we should choose it doesn't have any effect on the drug. It's enhance the solubility, right? Or stability as well. Okay, and it doesn't have you cannot take any material which can harm your body. You take the drug and capsule or make amorphous solid dispersion with any polymer which can harm to your body. No, we choose a polymer which is harmless. It does enhance the solubility and bioavailability and stability, right? Okay, so this is API, your drugs, and this is your polymer, and then you have amorphous solid dispersion. Amorphous solid dispersion is one of the most promising strategies, okay, to improve the oral bioavailability of your sparingly water soluble drugs, because some drugs are very, very good, right? Very, very potent, but they have problem. They are not very good they don't have very good solubility. They're not soluble, right? So they are sometimes they are not fully soluble. So they are called sparingly soluble, water soluble drug. So this ACDS techniques can make them fully soluble, or they enhance their oral bioavailability as well. Okay, because all the time we cannot take the IV, we cannot take the injections, right? So prefer to have oral drugs, right? Even nowadays we are hearing there are some very soon the patient don't need to have the insulin to inject the insulin every day. They have to insulin morning and evening. It's very painful, right? So they are going to have some drugs which can be taken orally, so it's easy for them as well, right? So solubility of a compound in the amorphous form is higher than the more stable crystalline form, because if they are in crystalline form, it's not very good, but if they are in the amorphous form, right, so their solubility is higher as compared to their crystalline form, because normally the crystalline drugs are stable, amorphous drugs are not stable, right? But with the help of amorphous solid dispersion, they are trying to have more stable and more soluble drugs. Okay, that's why the solubility of a compound amorphous form is higher than the stable crystalline form, because the Gibbs free energy is higher. So for the amorphous solid dispersion, the Gibbs free energy is higher as compared to crystalline. What is Gibbs free energy? Okay, you note down this all this terminology. You will also go through this Gibbs free energy, right? Okay. So what is the question? Can I? Who was asking the question?
I am Doctor.
Can you repeat your question, please?
If a substance is hydrophobic, does it automatically lyophilic?
Is the substance is hydrophobic?
Phobic. Is
Okay.
it automatically lyophilic?
Okay. I think it's not compulsory if the substance is hydrophobic, it is lipophilic, or maybe it can dissolve in any solvent organism. Your question is like that, is it or not? Right?
Yes.
It's
Yes,
not
sorry that.
it's not compulsory. Sometimes substance because most of the time the nature have two options, right? Either it is hydrophilic or it is hydrophobic. I can say yes, if it is not it is hydrophobic, it can be lipophilic, yes, mostly, right? But did you find any examples?
No, I don't find any example, but I just thought about it.
Hmm. I think is yes, if the substance is hydrophobic, most of the time it is lipophilic, right? Because when we are doing research, what we say, we just use see the solubilities in different solvents, right, including water. So most of the time it's dissolved in water, but sometimes no. So it has some suspensions, right? Okay, and if sometimes it goes into aqueous layer, sometimes goes in some drugs, some compound goes into a non-aqueous layer, some goes into aqueous. So if it should have either one's option, right? Either phobic or philic, right? Okay. I will search your question more, and I will let you know maybe in next lecture further. Okay, right? Inshallah. Okay, so the same thing here. Okay, so what is that? So in order to stabilize the amorphous drug excipient, in order to stabilize the amorphous drugs, excipients, right? What I say already, the polymers, right? The polymer, the coating. We coat the drugs are added to create a solid. When we coat the drugs with some excipients or often we use the polymers, and then we create a solid dispersion of drugs and polymer, right? Mixture. So the goal is to create a uniform miscible. So what happens after this? We have uniform miscibilities or dispersion where the drug is dissolved, okay, in this polymer matrix, and which is also known as solid solution. physical stability of amorphous solid drug. Okay, this is very important. The physical stability of amorphous solid drug is governed by thermodynamics. Okay, so how we can say the amorphous solid drug is stable physically? It is on the basis of its thermodynamics, kinetics, and drug excipient interactions, right? Uh, but how it goes into the body, it works, all this kinetics, and it goes into the body, release energy and absorbs. This is thermodynamic, and is a drug excipient interaction as well. Okay. Further, amorphous solid thermodynamic properties are governed by the drug heat of fusion, degree of supercooling, and configurational entropy, right? Whereas the kinetic contribution to this ASD physical stability are also associated with the translational, vibrational, and rotational modes of motion. Because all these drugs, when they go inside, they have because when you are on the earth, right, on universe, you move, right? Everything is moving. Most of the animals, humans, right? There are different type of motions, and this is maybe you have done in your physics, right? Different kinds of motions, right? Kinetic, translational, vibrational, rotational modes of motion. Same, the drug also have all these properties, right? The stability, the stabilization confirmed by the added, okay. What we increase the stabilization, right? How we increase? By the adding the excipients, right? Okay. So what happened when we add excipients to increase the stabilization? It result in a reduction of the dispersed drug activity due to the dilute effect, or favorable drug excipient intermolecular interactions, which in turn impact the thermodynamic and kinetic properties of amorphous. So what does it mean? When the stabilization we increase, how we do? We add the excipients, right? After we add the excipients or the polymers, okay, what it results? It results in the reduction of the dispersed drug activity due to the dilute effect, okay, or the drug excipients intermolecular interactions. Okay, either it can affect drug dispersed activity or drug excipient intermolecular interactions, and which in turn also impact the thermodynamic and kinetic properties of amorphous solid amorphous drug in amorphous solid drug, right? Okay, properties. Okay, I can show you one slide so you can understand better. You can see here. Okay, but I told before, so you can hear, you can see. Okay, you can see here. This is solubility, right? So it increasing, solubility is increasing. Overall, we are looking for the solubility or absorption. Okay, so here you can see. Can you see my cursor? Can you see the cursor? Okay.
Yes.
This is the cursor, the crystalline, and this is the amorphous, right? Okay. So this is tryptophan. This is tryptophan. They are using this tryptophan as a. Anyone can answer me why they are using this tryptophan?
As excipient.
Good. As excipients or polymers, right? Okay. So this tryptophan, and this is your drug of fluoxetine, right? Okay. So they are going to coat this decrease the stability or bioavailability of the drug of fluoxetine. They use this. Maybe I can. Okay. So they are using this excipients, tryptophan, for this of fluoxetine. So you can see here, when it was alone in amorphous and in crystalline form, the solubility was very low. The solubility was very low, even less than 5. So only the 5 milligram per ml was only have solubility. But once they have mixture of co-amorphous, for example, the main is the co-amorphous. You can see here what happened. In the co-amorphous form, as we done on ASDS, okay, you can see the increase. The tenfold solubility is increased after we have excipients. Previously, it was less than 5. Here you can see is around 4. And after we have excipients, it is going high until 30 milligram per ml. So it's tenfold increase in the solubility. So all this physical stability of amorphous solid drug is governed by thermodynamic, kinetic, and drugs excipient interactions. So what is inside going on? The inside story is all depends on thermodynamics properties, kinetics, right, and drug excipient interactions. So here you can see just the examples. Solid state interaction here, right? So how it works, because they have ionic interaction, positive negative interactions. Okay, so for example, this is your theophylline, right? And you can see they have pi interaction because of this excipients. Because this the excipients, for example, here urea, you can see have hydrogen bonding or pi interaction or ionic interactions, right? They can have ionic interaction, they can have hydrogen bonding interaction, or they can have pi. There are 3 types of interactions: ionic, either ionic, if they're positive, negative, and they have ionic interactions. If they have oxygen and hydrogen here, they can have hydrogen bonding. You know what is hydrogen bonding, right? So this is the hydrogen bonding. Okay, this is called weak bonds, hydrogen bonding. And you have either you have, because they have make the layers pi interactions, right? Okay, so here for the theophylline, you can see for this theophylline, they can have pi interactions. So all these excipients, they have the drugs to absorb or increase bioavailability due to have this type of solution state interactions, either ionic, pi or hydrogen. So it means this amorphous solid dispersions help us to increase the bioavailability, and it comes under supersaturating drug delivery system. Supersaturated drug delivery systems can help via amorphous solid dispersions, right? Okay, so do you understand until here? Is clear up? Okay, how? Wait, are your questions? Where is the question? Can I see the question again? Where is the question? Can you speak out the question, please? Can you speak out the question, please? Unmute and speak out the question. Where is the chat box? Cannot see the chat box. Hello? Okay.
How that try to fit can make of the
Can you speak out your question, please? I cannot see the chat box from here. Wait, chat box. Okay, got. Okay. How tryptophan can make afloxacin become amorphous? Tryptophan disrupt the bonding in afloxacin. Okay. Wait, I go to previous picture. Okay. Okay. This is afloxacin, right? And this is tryptophan. Okay. So, you know, this is no chemical interaction between afloxacin and tryptophan. Okay, this one you keep in mind. There's no chemical interaction between ofloxacin and ofloxacin. Have you eat the burger? Have you eat the burger? What happened? You bun up, down, and in between you have your kebab, right? So it's same like that, okay? It's just a sandwich type, okay, right? You have, you can feel a taste of burger, you can feel it, feel the taste of kebab, or you can feel the taste of your bun, right? Okay, it just protect and help to bring in a stable form until the site of action, right, where it has to go. For example, if you are not feeling very, for example, if there's some danger outside from your home until school, right, or your college, university. So what happened? Your parents or your guard bring you, shelter you, and bring you until the your college or your university. Okay, right? Okay, he don't go inside. He don't read with you, right? He don't have an interaction with you, but he just help you, right? It does give you shelter. Same the excipient. That's why it's a good question. That's why we have to select the polymers or excipient. It doesn't have any interaction with your drugs, right? It just protect, it just cover, it just shield, and it just safely your drug arrive at the destinations and it can work well. Okay, with the help of this excipient, it can easily, when you take orally, and it increase the solubility of a drug can reach until the destination or the point where you have to interact with the receptors. Okay, right? So this is the work of excipient. They don't do to any interactions with the drug itself. If they do any interaction with the drugs, no point to take the drugs. Okay, it will not, they will just play with each other, they just do interaction with each other, they don't do their assigned job, or they don't reach the target site or where the disease is there. Okay, so no point. So that's why we choose the polymers or excipients which doesn't have any harmful effect or doesn't have any real chemical interaction with the drug itself. Okay, right? So did you understand, Akmal? Akmal, did you get my point?
Yes, doctor.
Akmal,
Yes, doctor.
okay, did you understand or not?
Understand. Yes,
Huh?
very understand.
Okay. Okay, so the next, okay, you can stop me anytime and you can ask question. I don't want to be finish all the slides and you don't understand anything. I don't want to be like that, right?
Okay.
If I finish only out of 24, I can finish 10 slides is also no problem for me. I just want you should understand. Okay. Now we come.
Doctor,
Sorry.
is it that only the API can permit the membrane, and then it will dissociate from the excipients from the bond? Is it?
Sorry, API. I don't understand. Is it only API?
Is it only the API
Hmm?
can pass the membrane?
It depends because the main
Because you said
interactions.
just now that the excipients are just like the shelter for the API, right?
Carriers or
Yes.
shelter or shield, right?
Okay, for the and then for
And
the drug
also
absorption.
it also helps in interact. Sometimes it also increase the drug receptor interaction sometimes, right? Because they also have some charge, right? So they also help to the drugs to interact with the receptors, right? Not only the solubility, they also help sometimes because because you can see the enzymes. It's just a pocket light. All our body enzymes just a pocket light or receptors, right? So they have the pockets or pouch, whatever, right? So because they also have some, you see here, they have, I showed some type of interactions they have. So it also helps to help in the drug receptor interactions. Okay, just like our parents, they help us from the beginning until the end, right? Sometimes excipient help until the end, sometimes where it necessary, right? Okay, that's why we cannot simply take the excipients and just give them drugs in the market. These are research. They have some excipients which they say they are inert. Inert means they don't chemically react, right? Okay, they don't chemically react with our body and give some harmful effect. So we just select if they react, but they don't have any harmful effect, and they have until drug receptor interaction as well. Okay, maybe okay, you know, your tutorial will be based on this type of questions. Okay, so you also try to find some research, some literature, and for your coming tutorial will be based on all these types. Okay? Because for your tutorial you have to discuss all the this properties, mainly Dr. Honey's teach you, and I'm teaching on the basis of thermodynamics, solubility, and bioavailability, right? And for example, you choose any drugs and you show how they increase the bioavailability, what type of for this API, what type of excipient they use, and the viability decrease. So I'm very happy you are asking this type of questions, because this type of your brainstorming will help you in your tutorial as well, right? That's why we have designed the tutorial, so you can fully understand all the properties, either it is bioavailability, solubility, stability, or acid-base properties of the drugs. And even you have to keenly see the drugs, what type of bonding in the drugs your drugs have, what type of hybridizations are present in your drugs. So this will Dr. Ibtisam will teach you in week 5. That's why we have tutorial after week 5 in week 6. Okay. For example, you select any drugs, maybe this ofloxacin you select, and you show us which type of but don't select this drug, because already I have given that lecture, and you just find what type of bonding they have, what type of hybridization is present in this drug, what is the bioavailability, the absorptions on the basis of thermodynamics, right? And drug receptor interaction, if you can just more explain. And for the another thing, I will explain you in the what type of things you want. Okay, so you have to divide yourself into 5 or 6 members per group, and you have to give maximum 15 minutes presentations. But you are in the group, so you just divide a task. So you search for these three topics, and then you combine all in one poster. Okay, and you have to present this poster on week 6. And I'm giving on this is your choice, which drug you choose. Okay, so this will enhance your knowledge, this is enhance our knowledge as well. Okay, and this will help you in future as well when you go with your pharmaceutics. Okay, right? Because in pharmaceutics, this type of properties you have. Okay, so thermodynamics. Some student wants to come. It's already there or not? Okay. What? So now we come to thermodynamics. Now we have an actual topic, thermodynamics. The term, now you have to understand what is thermodynamics, right? Because you have heard this type of terms, thermodynamics, entropy, gives free energy. So now you will know what is this thermodynamics, what is this entropy, what is enthalpy, what is gives free energy, right? Okay. The term origin from the Greek words. The term origin from the Greek words therm. Therm means heat. Okay. Dynamics. Dynamics means power. Okay. So this is a branch of natural science concerned with the heat and its relation to other forms of energy and work. So because it's concerned with the heat. Okay. Because when we take the drugs and we have heat release, and it helps in the absorption of our drugs. Maybe I have one article, small article, maybe I will give you by the end of next lecture. Inshallah, I will post, right, with my lecture slides. Okay. The study of the energetic of physical, chemical, and biological reactions of transformation. So all the study of this energetic of physical, chemical, and biological reactions or transformations. Okay. And energy transfers. Okay. At the beginning, I ask you when you have cup of tea, right? Okay. And after some time, it becomes cold, right? Okay. It becomes less hot. Okay. So this is the heat transfer. The energy transfer that can be strictly dissolved into two distinct components. When the energy transfers, so either it is transferred in the form of heat or either any work done, right, is specified by macroscopic variables. So all this heat transfer is work is done macroscopic. We have two types, microscopic and macroscopic. So these are macroscopic. Okay. It is a branch of science that deals with the properties of matter as related to change of temperature. In this branch of science, in which the matter change the temperature, same again, cup, what happened? Temperature change. For example, if I have a cup of tea hot, you check the temperature, it's around maybe 70 or something like that. After 10 minutes, the temperature reduce. Again, check with thermometer, the temperature reduced, right? So what is change of temperature? So it's the branch of science that deals with the properties of matter, which is related to change of temperature or degree of hotness, right? Zeroth law of thermodynamics. If two systems are in thermal equilibrium with a third system, they are also in thermal equilibrium with each other. For example, you have A, B, and C, right? If A is in equilibrium with B and B is equilibrium with C, it means A and C are also in equilibrium, right? Okay, because two systems are in equilibrium, thermal equilibrium with a third system, they are, so third, for example, third is B. So A is equilibrium with B, C is also equilibrium with B. It means A and C are also with equilibrium with each others. Okay, so, or you can say if A and C are each in thermal equilibrium with B, A is also in equilibrium with C, same time. Okay. Are still coming in. Okay. Okay. The language of thermodynamics. To understand the law of thermodynamics and how they work, first we need to get the terminology right. Some of the terms may look familiar as they're used in everyday language, but their meanings are more technical and precise. Because in our surroundings, very thermodynamics properties we can see, but we don't know. As a in technical, in precise way, we don't know, right? For example, you previously don't know your cup of tea is also mentioning examples of thermodynamics, right? But you know now when you have all this terminology. Okay. Okay. For example, system. We have three things mean here: system, surroundings, and universe. If you understand system, if you understand surrounding, we can understand universe as well. So what is system? System is region where we focus our attention. For example, see in this diagram, the block AU, this is the system. This is the system, right? Is a region where we focus our attention. For example, my focus or your focus on this block. Again, if you have cup of tea on your table, you are going to watch, is it cold or hot? I want to see after how long it remain hot. So your system is your cup of tea, right? Or cup of milk, whatever, right? Okay, or milk of Milo, whatever, right? Okay. So your system, because you are focusing on this cup, so it is hot or cold or how long it remain hot. This is your system. Same, the block of O is your system. Surrounding is the rest of the universe. The water bath or constant temperature. Okay. For example, you keep your cup inside some ball or inside some water bath. Maybe you want to keep it hot, or you're just some, if not water bath, maybe surrounding of your cup, right? Okay. So for example, in this diagram, this is surrounding. Okay. For example, you can see here this block A is inside this water. This blue color is water. So this is yellow is your system, and outside of this block is water. This water is the surrounding. Okay. So surrounding is the immediate neighborhood. What is surrounding is the immediate neighborhood. For example, your cup surrounding is yourself, or yourself surrounding is cup, right? Okay. If I ask cup what is its system, it will say the person is my system. Okay, my focus is on that person. If I ask person, he say my focus is on the cup. So this is my system. And for the cup, the surrounding is person, or for the person, surrounding is cup, like that. So here the surrounding is water and the system is the block A. Okay. So what is universe? Universe is system plus surrounding. When you combine both system and the surroundings, it is considered as universe, right? The part that is within the dotted line box in the figure is universe. Okay. So all this boundary, you can see this red color boundary, the dotted, this all together is universe. This part is surrounding the blue one. The yellow part is system, and system plus surrounding, all this boundary inside is the universe at large. Okay. More practically, we can consider the surrounding as the immediate neighborhood of the system, the part of the universe at large with which the system effectively interacts. Okay. Where the system can interact is called its surrounding. Until it can interact is called its surrounding. Okay. In this scheme of the things, we can visualize a system, the surrounding, and the universe at large. Okay. Things that matter for the surroundings. Okay. So what things can matter in the surrounding plus the system? Temperature, pressure, ability to do work, transfer heat, right? Transfer matter. Okay, either matter can transfer, either heat can transfer, temperature, pressure, right? Parameters for the system. What are the parameters? Internal energy, enthalpy. Again, the enthalpy you will see later on what is enthalpy, right? Okay. Temperature and pressures. Okay. So this is another diagram. Okay. You can see this system. This is the blue is surroundings. Okay. All the matter in the universe. Okay. Surroundings. This is boundary for the systems. Okay. Right. Now, we have different types of systems. Okay. Open, closed, and isolated. This is also important. To a thermodynamic system, two things may be added or removed in any thermodynamic systems. Okay. In a system, so you already know what is system, surrounding. and universe. So in a system, for example, again, you can see this, you can consider this test tube, or you can see your cup of tea. Again, you can take your cup of tea, right? Okay. A glass of water also can. So to a thermodynamic system, two things may be added or removed. For example, energy in the form of heat or work or matter. Energy. Okay. So as I told you, a cup of tea is hot. After half an hour or 1 hour, it becomes cold. It means the energy is transferred from the cup. Previously, the cup was hot, but now it's not too hot. So energy is transferred from the cup to the surroundings, right? From the cup to the surroundings. And when you have cup of tea, it's not like that. You don't drink. Okay, what happened? You keep here, you drink also. So the matter is also transferred. Matter is also transferred to the surrounding, because you are in the surrounding. So you take the tea, you drink the tea, right? So matter is also transferred, and energy also is going to transfer, right? Okay. So it may be, or what happened? You have half cup of tea, you add more tea inside. So either you add or either you drink or remove, same. Okay. So two things from the system, either energy or matter. Open system is one to which you can add on. If it is open, your cup of tea is open, right? It can be, your heat can be add or remove. Either you can say your from hot it's going out, it's become cold, and your tea also you are drinking. Okay, right? So this is an open system. For example, here, this is, you see, this is open system, and exchange of mass and energy is easy here because it is open system. So interaction of thermodynamic systems, type of system: open, closed, and isolated. You see, mass can flow, work can done, or heat also can add or remove, right? Okay, this is open system. The second is closed system. A system which you cannot add matter is called closed. Okay, here you can see this is closed. You have just make a cap. Now exchange of energy but not mass. Okay, it is when you have cup. Okay, you just cover. Okay, you cover it either in a bottle. Okay, you take out the bottle from the fridge and keep outside. It's very cold when you keep outside. Still it has cap. You drink. Okay, no, if you have open, you can drink. If you keep it closed, allow nobody should drink. I have closed the cap. Okay, you keep on the table, and after sometimes you come, it's not cold as you leave it before. It is, the coldness is decreased as you take out from the fridge. It's very cold. Or you can say, if you fill your bottle with hot water, cap, and keep on the table, after some time you come, it's not very hot, it's a bit cold, right? So heat is transferred, but the water you fill up in the bottle is still there because you kept. Don't allow anyone, don't open the cap, just leave it. Okay, but you cannot control the transfer of heat. It was cold, but it is plastic bottle or glass bottle. The heat is transferring. Okay, heat can transfer, but the matter is inside. The level of water is still there. Nobody is taking the water. But if you leave it open, you drink, you drink because it's open. You allow. Okay, you can do. Or sometimes it evaporates. If you have solvent, but the water don't evaporate, right? Okay, it's very easily. Okay, so for the closed system, you keep, and the heat is transferring, but the matter is still there. Matter is still there. It means this is called closed system. So in the closed system, mass flow, no, because the cap is closed. Work is going on, yes, because if the heat is going out, the heat is the temperature is decreasing, it means work is done. Okay, so if the heat is decreasing or increasing, right? But here decreasing, right? Or hot also or cold, so the work is done. The third system is isolated system, a system to which neither matter nor heat can be added or removed. If the heat cannot be added, if the matter cannot be added or removed, it is so no work is done. This is called isolated system. In the isolated system, you can see this black color. It becomes isolated. You see the thermos flask, the very good quality thermos flask, and we just keep the hot things, and when you open 2 or 3 hours, it's still hot. Or you have very good thermos flask, and you keep your cold water, and when you open, it's still cold, right? And you keep close, and when you see the matter is also there, same level, and the heat is also, you can feel, or coldness if you have cold thing, still. So it is isolated. It means neither the heat, neither the mass flow, neither heat, so no work is done overall. Okay, so the example is a closed vacuum thermostat, because we have vacuum here, right? So this vacuum help us to it doesn't allow to come heat from the outside to enter the flask, or from the inside flask doesn't allow to go outside, transfer any heat from the inside to outside or outside to inside. That's why the temperature remains same for this insulated system. The best example is thermos flask, a closed vacuum thermos flask. Okay, but this is uninfluenced by their surroundings. There's no exchange, neither energy nor mass. For the closed, exchange of energy, but not mass. For open, exchange of mass and energy both. Okay, clear? Okay, so you can see here, open system is very daily examples. When you boil water or anything, so all this exchange. Here, close, only the energy exchange. You see, it is closed, right? So matter does not go nor out or not in. Okay, only the heat energy is transferred. For the isolated system, you can see this one. Neither energy nor heat nor mass. So it is called isolated system. Okay. This is again the system and the surroundings. So you can see homogeneous system. What is homogeneous system? Okay. And you have good solutions. This is homogenized. Okay. And if you have heterogeneous system, consists of 2 or more phases. So you can see suspensions, or sometimes you have supernatant and precipitate. This is called heterogeneous solution. Homogeneous is homogeneous, same phase, right? Okay. So for the energy, the capacity to do work, everybody know what is energy? The capacity to do work or to transfer heat. Either transfer heat or to do work is called energy. Okay. When energy is transferred from one object to another, it appears as work. Okay, that's why we say when the energy transfer from hot to cold, whatever, right? So it appears as work or as a heat. Okay, chemical or physical change either. Okay, either we have chemical or physical change, or either kinetic versus potential energy. Okay, either we motion. Okay, we have do some work, or we change our positions. So this is position potential energy. So this is a type of energy. Okay, you can see it's same here. Types of energy: potential energy, thermal energy, kinetic, chemical. Same the type energy of the thermodynamic systems. Total energy of body is equal to thermodynamics plus mechanical. Whatever we have inside, thermodynamics energy comes out, and we do some work. It's called mechanical energy. So as a result of mechanical energy, we do some motion, some work, or some change, position change, right? Or thermodynamics, which is inside, we have kinetic for transmission and energy. We have already done this type, okay? And vibration, rotational, electron. In the first few slides, we have this type of thermodynamic energy. This is produced in our body, right? Okay. As a result, we do some kinetic and potential or mechanical energy. Okay. So what is first law of thermodynamics? Now it comes to the first law of thermodynamics is the law of conservation of energy. Energy can neither be created nor destroyed. We cannot create energy ourselves. We cannot destroy. Only transform one form to another form. Okay, we cannot create and we cannot destroy. It doesn't destroy. It converts from one form to another form. Okay. For example, the heat which is come out of the hot cup of tea is not destroyed. If the cup becomes cold, doesn't mean the heat what was inside is destroyed. No, it's transferred to surroundings. Okay, and convert into another form, right? Okay, so it is the transfer of one form to another form. The increase in internal energy as a result of heat absorbed is diminished by the amount. Okay, if we, for example, when we take some food, we have energy, right? So once we have energy, we do some work. It means the energy is one form we take and converts into another form, and we do some work. Okay, and we do some work on the surroundings. Is it? The heat, by convention, the heat added to the system. If the heat is added to a system, or heat absorption is always positive, and work done by the system. Okay, and if we take heat and absorb delta Q, it means it is absorbed and it is positive. And when as a result, we work done by the system, delta W on the surrounding, this is called, comes in negative. Okay, absorb positive, release or done negative. For same endothermic, we always take positive. Exothermic, we take negative. Okay, so the application of a force through a distance. Okay, work done, we have some force, we do some distance or cover distance. So this is work done. Force is, this is the force unit. This is the this is distance unit, meter, right? So force force is equal to, the force itself is equal to mass, okay, kilogram into acceleration, meter per second square. So this is the force unit, which is normally equal to, force unit is Newton. Okay, so instead of all this, we can use as simple Newton, right? This is distance, meter. Okay, right. Translation energy. Okay, and a reaction usually exchange energy with the surroundings into forms as well. Normally, reaction or we exchange energy with the surrounding two form. Either we do release the heat, or either we do some work. Energy transfer, for example, energy transfer from a tennis racket to the ball. When we play the tennis, what happened? The tennis, we used hit and we hit to ball. So what happened? The energy we give to tennis is transferred to ball. Okay, our energy which is given to the tennis racket is transferred to our ball, and the ball go far, right? Sorry. Energy transfer from burning or natural gas. Okay, when we cook some things on a stove, electric or gas stove, so what happens? The energy which is in the stove is transferred to your food, or your food is cooked, right? Or your anything you want to warm or heat, boil your water. So your energy in the stove or gas or whatever in the electric, using electric induction cooker, or you using the gas. So this energy transferred to your food or your water, whatever, right? Okay. So for the directed motion to work, we have an object against a force, and random motion. So temperature change is a random, right? This one is same. Transfer energy as a result of temperature difference between one system and the surrounding. Same, I ask you why your cup of tea becomes cool after some time, because your surrounding is not hot. Your surrounding temperature is less. Your temperature of your cup is high. Okay, because there is difference of temperature. So until the temperature becomes same or equilibrium, the heat will transfer. Okay, you just do one test yourself today, experiment. You just take a hot cup of tea and check the temperature, and your surrounding temperature normally 28 or 30 degrees centigrade. You just allow your cup for 1 hour or half an hour there, and you check after some time the surrounding temperature and your cup temperature, either it is water or tea, will be same. So transfer of energy as a result of temperature difference. So there's a definite temperature difference in the surroundings and in the cup of water or tea. That's why that heat transformed from this high temperature to a lower temperature to the surrounding, because surrounding temperature is low. It will be transferred until it becomes same, right? So transfer of heat energy as a result of temperature difference between one system and surrounding raises the temperature of a surrounding objects. So that's why energy you can see here from the system, heat is transferring to the surrounding and increase the surrounding temperature. Okay, for example, if you are in cold weather and you use heater, okay, the heater is your system and you are feeling very cold. And when you switch on the heater, after some time, your surrounding, you feel very hot. So what happened? The heat is transferred from this heater to the surrounding. Okay, right? And once, if you allow the heater to heat until 30, because your surrounding temperature is around 10, for example, and you want 30 around or 25. So once it's become 25, so it will be feel temperature of your surrounding, which was cold before, it is around 25 again. Okay. So this is a transfer. So what do you want? I should stop here. Just give me how many slides we have. Oh, we have many slides. Okay. I just finish. Let me finish just 1 or 2 slides more, right? Okay. But after this, I have to give you about. Give me 5 minutes, 6 minutes more. Okay. Heat change. Okay. The heat change you can see here, which is the transfer from hot bodies to cold. Same. Okay. This is the whole hot. This is cold. Transfer from the hot to the cold. Heat transfer into the system from hot surrounding is positive. So you see transfer from hot surrounding is positive. Heat transfer by the system to the cold surrounding. Heat transfer into the system from hot surrounding is positive. Heat transfer by the system to cold surrounding. If heat transfer by the system to the cold surrounding is negative, heat transfer into the system from hot surrounding is positive. If your surrounding is hot and it is transferred into the system, it is positive. If heat transfer by the system to the cold surrounding, it is negative. Okay, this is very good examples. You can see block A, the first one you see here. Huh? Block A is hot. This is block A. This is block B. Block A is hot and block B is at room temperature. So hot is showing by red and the room temperature by blue. You can see this is temperature 98 and the temperature of block B is 27, right? So block A is hot, block B is at room temperature. What will happen if the two blocks are in direct physical contact? If you keep them in direct physical means close together. Physical contact means close together. Block A, block B. This is hot, this is cold. Okay, you keep them like that. So what happens? Heat energy is transferred at fast rate from hot to the cold. Okay, because this is low, this is high. This is high temperature. So from here, red to blue, there will be fast. Okay, the heat flow from the hot to cold will be fast. Heat is transferred at a low temp rate from B to A. On contrast, from the cold to heat to hot, it will be slow. Okay, it will be slow. And from hot to cold, it will be fast. Okay. What happened after some times? What happened? After some time, both will have same rate. The heat is also transferring from hot to cold. Heat is also transferred from cold to hot. But the transfer of from hot to cold high here because this temperature is high, this temperature is low. So what happened? After some time, the temperature becomes 37, not 28, not 27. It will be 37. Why 37? Okay, because the heat is transferring from hot to cold, but the heat also transferring from cold to hot. Okay, so but the transfer from cold to hot is slow. That's why it is not much increase here, right? But there's much decrease in hot temperature. From 98, it decreased unto 37. Why? Because there's a fast or more transfer from the rate is to transfer from hot to cool is higher. That's why it decreased to 37. Okay. After some time, heat is transferred at the same rate. So what happened? After some time, the rate becomes same. Okay, the net rate of heat transfer between the two, and once it becomes equilibrium, same temperature, so there will be no transfer of heat. The temperature of block A and block B becomes equal. Molecule, both objects have the same energy after some time. Okay, because they have same flow of heat. Right. Okay. What is going on? What is happening? Because the hot object A release heat, while the cold object B absorb heat. The temperature of block A decreases. The temperature of block B increases. The heat transfer to B increases the kinetic energy of its molecule. The net result is a transfer of heat energy from the hot. Net, what we will say? Net, what is going on? The transfer of heat from the hot to the cold. Because at the end, there's slight increase of temperature of cold, right? So the net is the transfer of heat energy from the hot to the cold. There's no decrease in the temperature of the cold, right? The cold, they increase the temperature, but the hot, there's a decrease of temperature. Okay. Thermodynamic, okay, now it is, you can understand the equilibrium. Thermodynamic equilibrium, a system whose observable properties are not undergoing any change with time. All parts of the system at the same temperature. So at the equilibrium, you cannot observe any change. All look at same temperature, right? So all part of the system at the same temperature. The composition of the system is not changing. That's what is called equilibrium. There is no macroscopic movement of materials in the system is heat and temperature, right? So thermal equilibrium, there is no net flow of heat between two objects. Two objects have the same temperature. So you can see here, okay, same object 2 and 3. When two objects are separately in thermodynamic equilibrium with the third object, they are in equilibrium with each other. If this object 2 is in equilibrium with 1, 3 is in equilibrium with 1, it means 2 and 3 is also in equilibrium with each other. This is called zeroth law, when all process is in equilibrium. Okay. So we will start from here next week, right? Okay. And then we will go to up to the second law, thermodynamics. Okay. Yeah, we have few slides here. And for the next lecture, we don't have much slide, maybe 20 slides from next early. Okay. So maybe I stop recording here. Stop. Okay.